Welcome to the AI Research Roundup. I'm Alex. Today we're looking at this paper from the Hugging Face Trending List, published on October 8, 2025, just yesterday. The headline is a unified framework that makes reinforcement learning for vision language action models both standard and fast, with a single model scoring 98.11% on 130 LIBERO tasks and 97.66% on 25 ManiSkill tasks. The paper is titled RLinf-VLA, a unified and efficient framework for VLA+RL training, and the implications for model training are quite significant. Beyond accuracy, the system's hybrid fine-grained pipeline yields 1.6, 1 to 1.8 times speedups, supports multiple simulators and algorithms, and even shows stronger zero-shot transfer on a Franka robot. Also, the authors shared a robust GitHub repo. You'll find the RLinf codebase with modular training pipelines, PPO and GRPO implementations, quick starts and example gallery for VLAs on ManiSkill 3 and math reasoning, multi-backend support via FSDP plus Hugging Face and Megatron plus SGLang, an async VLLM worker, auto-scheduling, plus docs, Docker setups, tests, and ready-to-run scripts. Figure 1 shows the end-to-end framework that unifies models, simulators, and reinforcement learning algorithms. The top band summarizes supported components across OpenVLA variants, ManiSkill and LIBERO, and PPO or GRPO. It highlights 3 GPU allocation modes, which coordinate simulation, rendering, inference, and training to raise utilization. The hybrid pipeline delivers roughly twice the throughput in practice. The bottom panel reports near-perfect simulated success with a single policy, and photos on the right illustrate real robot trials that succeed under distribution shift because the reinforcement learning policy generalizes beyond supervised fine-tuning. Figure 2 shows the basic training loop that connects rollouts from the simulator and policy generation to the learning step. A rollout means collecting experience by acting in the simulator, which produces observations that the policy turns into actions. Those actions feed back to the simulator, and the resulting trajectories move to training, so the policy updates. The dashed path indicates that new weights flow back to generation, closing the loop for the next round. So, Figure 2 showed the training loop. Figure 3 contrasts how GPU allocation shapes efficiency. The co-located mode packs simulator, generation, and training on the same devices, which maximizes sharing but risks memory contention. The disaggregated mode isolates components per device, so idle gaps called GPU bubbles can appear. The hybrid with fine-grained pipelining splits the simulator into small stages that feed generation and training in sequence, which keeps each device busier. This design sustains utilization because queues coordinate handoffs and offloading stays predictable. So, Table 2 summarizes ManiSkill results and shows that reinforcement learning drives large gains over the base models. Out of distribution means testing under novel conditions that differ from training, which stresses generalization. OpenVLA RLinf-PPO reaches an average near 82%. OpenVLA OFT RLinf-PPO hits about 98% in distribution. The same OFT model records roughly 92% on out-of-distribution vision, indicating strong transfer. Okay, Figure 8 reports throughput and shows that hybrid allocation with fine-grained pipelining delivers the highest speed across scales. Fine-grained pipelining means splitting simulation and training into stage steps so each GPU stays busy. The two-stage variant gains about 1.9 times over the disaggregated baseline at small scale. As clusters grow, co-located and hybrid modes remain strong because they reduce idle gaps from model loading and state switching. Wrapping up, 2 takeaways stand out. The framework standardizes reinforcement learning for vision language action models while delivering real speed and quality gains, with hybrid fine-grained pipelining boosting throughput about 1.6 to 1.9 times and near-perfect simulated success. The broader implication is faster, fairer progress toward robust embodied agents that transfer to real robots. Thanks for listening. I am Alex, and this was the AI Research Roundup.